pipe in the form of T or other. And the last disturbance in the pipe is entrance and exit. Okay, so those are also under the category of minor losses. So I start with the first one, the minor loss due to sudden enlargement. Okay, now say we have this pipe. At this section, it is suddenly enlarges. Okay, so this is the direction of flow. Okay, so I consider here two sections. One is at the entrance. So this is my section 1 and this is the section 2. Okay, so when liquid coming out from this end, it take a shape like this. Okay, so the water coming out from this pipe and take shape like this. Okay, so in this region you can see the air is entrapped. So that air is under circular state. Okay, so I have two sections now, section 1 and section 2. At section 1, I say the area is A1. At section 2, the cross-sectional area is A2. Okay. Velocity, average velocity at section 1 is V1. Average velocity at section 2 is V2. The pressure intensities at section 1, that is P1. At section 2, it is P2. Now here one additional part at the top, this one. Okay. So at this part, say the pressure intensity is Px. So this is the pressure intensity acting on this liquid. ये यहाँ पे है. Okay, that is Px. So now I use here impulse momentum relation. Okay, so I apply that relation on fluid element within section 1 and section 2. So I consider here only the pressure force. Okay, so you can write it as the pressure force on element between 1 and 2 should be equal to the change in momentum. Okay, so the pressure force I write. So at section 1, we have P1A1 plus Px into the remaining annular area, that is A2 minus A1. Okay, that is at section 1 minus P2 into A2. This is equal to the change in momentum WQ upon G V2 minus V1. Okay, so from impulse momentum relation, I can write the net pressure force on the element is equal to the change in momentum. So now I put here one assumption. The assumption is, let us say Px is approximately equal to P1. Px is approximately equal to P1. So now I write left hand side again. So when I write this again, so here I replace this Px by P1. So I write this relation again. So P1 A1 negative sign that cancels with P1 A1. So I left with P1 minus P2 into A. This is equal to WQ upon G V2 minus V1. Okay. Now I divide both sides by W, or you can say I take this W on other side. So I write it as P1 minus P2 by W should be equal to, now here is A2, is equal to Q upon A2 into G V2 minus V1. Okay. So this is the pressure drop now, P1 minus P2 by W from 1 to 2 due to this sudden enlargement. Okay. So further I write this Q upon A2. So A1 V1 is equal to A2 V2 is equal to discharge. Okay. So Q upon A2 I can write as V2. So I write it as V2 into V2 minus V1 divided by G is equation number 1. So this is the pressure drop from section 1 to section 2. Now I apply the Bernoulli's theorem at section 1 and section 2. So when I apply the Bernoulli's theorem at section 1 and at section 2, I can write V1 square divided by 2G plus P1 by W plus Y1 is equal to V2 square divided by 2G plus P2 by W plus Y2 plus the losses due to expansion. Okay, plus the losses due to expansion. So now I rearrange the terms. Now also here this pipe is horizontal. So that means Y1 cancels with Y2. So I write from here head loss due to expansion is equal to P1 minus P2 by W plus V1 square minus V2 square divided by 2G. So I put here the value of P1 minus P2 by W from equation number 1. So I write again HEXP is equal to V2 minus V1 divided by G plus V1 square minus V2 square divided by 2G. Okay. Now I solve this term and the resulting equation comes out to be HEXP should be equal to V1 minus V2 whole square divided by 2G. Okay. So this equation, with the help of this equation, we can determine the head loss due to sudden expansion. That is the one type of minor loss. So in this formula, you have V1, that is the velocity at minimum section. Okay. And V2, the velocity at the enlarged section, that is the maximum section. Okay, so care of that divided by 2G give you HEXP. Okay, now I can write this equation also into another form by using A1 V1 equal to A2 V2. So I find from here term V2 that is A1 upon A2 into V1, and put this value of V2 into this equation. Okay, so then I write HEXP again is equal to, so this comes out to be 1 minus A1 upon A2 into whole square V1 square divided by 2G. Okay. Now further this term depending upon the shape of the pipe. So I write it as one constant, that is KEXP into V1 square divided by 2G. So I write simply HEXP is equal to KEXP V1 square divided by 2G. So that means the one minor loss, that is loss due to expansion, I write as one constant multiplied by the head velocity head corresponding to the inlet velocity. Okay, this is the velocity head corresponding to the inlet velocity to the sudden expansion. So that is V1 square divided by 2G. Okay. So then I take the second loss due to sudden contraction. So in that the arrangement is something like this. This is the direction of flow. Okay. So when liquid coming out from this end, so that form due to inertia something like this. So liquid coming out from this pipe like this. Okay. Now this cross section of minimum area for jet, now the cross section is minimum over here. So this is called vena contracta. Okay. So now I mark three sections, section 1, section 2. Okay. The another section is section C, that is at vena contracta. Okay. So at section 1, I write velocity as V1. At section 2, velocity V2. At section C, velocity VC. Cross-sectional area at section 1, A1. At section 2, A2. At section C, AC. Okay. Now the main concept I use here to find out the minor loss due to sudden contraction is that when liquid coming out, okay, now at this section I divide this portion into two parts. Okay, I can divide this portion into two parts. One, when fluid is converging. The second, when fluid is diverging. Okay, at vena contracta, that is formed due to sudden contraction. So I divide that portion into two parts. One is the converging part, second one is the diverging part. Now the length of this converging part is very small as compared to the length of diverging part. In actual situation, the length of converging part is less, very less you can say, as compared to the length of diverging part. Okay. So on the basis of this concept, I can write that loss due to sudden contraction, the main contribution in this loss is due to the expansion from C to section 2. Okay? Are you able to understand? The loss due to sudden contraction, that is mainly due to the expansion of flow from section C to section 2. So now I write the loss due to contraction. I write it as SCUN. Now this loss is equal to, now see the formula, this one, V1 velocity at the start of expansion. So I write it as VC minus V2 whole square divided by 2G. Okay. So further I put here the value of VC. So I use relation AC VC is equal to A2 V2. Now further I have one more relation, that is AC, area of cross section at vena contracta, divided by area of opening, that is A2. I write it as CC, coefficient of contraction. Okay. So AC is only this area. AC is this area, cross-sectional area. Okay. So AC upon A2 I write as CC. So CC is coefficient of contraction. Okay. CC is coefficient of contraction. So I write here AC as CC into A2. So I replace here AC. So I write it as A2 V2 is equal to CC into A2 into VC. So I find from here the value of VC. So VC comes out to be A2 cancels with A2. So V2 divided by CC. So I put this value of VC into this equation. So again I write HCON, that is equal to, okay, so put here the value of VC. So that is V2 divided by CC minus V2, this term whole square divided by 2G. ठीक है, तो जो कुछ कॉमन आ रही है टर्म उनको आप कॉमन करिए, बाहर आ जाएंगे वो ब्रैकेट से. So I can simply write it as 1 upon CC minus 1 whole square into V2 square divided by 2G. Okay. Then further I can write it as HCON is equal to, now I write this term as one constant because again this term depends on the geometry of the pipe. So I write it as KCON into V2 square divided by 2G. Now you can again see this loss is one constant multiplied by the velocity head corresponding to the leaving velocity. Okay. So HCUN depending on V2 and HEXP is depending on V1. So on the same lines, I can write the minor loss due to bend, due to other fittings. Okay. On the same lines, I can write those minor losses also should be equal to a constant multiplied by the incoming velocity square divided by 2g. So any minor loss due to bend, okay, T in the pipe fitting or any other fitting, I write it as a constant multiplied by V square divided by 2g. So again, this constant depends on the geometry of that bend or fitting available in the pipe. Okay. Similarly, the last two, entry loss and exit loss. So for entry loss, the K factor I write as 0.5. Okay, this is for entry loss. Okay, and for exit loss, I write K as 1. Okay, the value of K for entry loss is 0.5 and for exit loss the value of K is 1. Okay, so these all are the formulas for minor.